But now to the technical program, I'm very happy to be able to announce our first speaker. Rupak Majumdar is a scientific director at the Max Planck Institute for Software Systems in Kaiserslautern. He got his PhD from Berkeley and since then did work in a very, very broad area of programming languages ranging from logic and automata theory to verification, hybrid systems, cyber physical systems, probabilistic systems. And today he will talk about testing. Welcome.
Thanks, Peter. Thanks for the introduction and thanks for the invitation. So I will talk about some recent results that we have had in testing. And this is mainly work with my graduate student, Philip Niksic, who is in the room there. And a part of it also with Dmitry Chistikov, who's now in Warwick. Okay. So despite many formal approaches, practitioners test their code. And to add insult to injury, they do this by just giving random inputs. And despite our best judgment, this way of giving random inputs is surprisingly effective in finding bugs. Right? Without naming names, I can tell you that if you have worked in formal methods, you have at some point given a talk or written a paper that says, testing is insufficient, we need cool formal methods. On the other hand, testing works. And in this talk, what we'd like to do is to explore this unexpected effectiveness. So let me give an example, right? So there's a tool called Jepsen. So Jepsen is a tool for testing distributed systems. So what it does is that it gives you some APIs to start a distributed system. You start a bunch of nodes. You have the network. And then it essentially introduces some network partitions at some point. And most of the time, these network partitions are introduced randomly, right? So it randomly says that these processes can no longer talk to these other processes. And then at some point, it recovers the partition and lets the system run again. Now, in distributed systems, there is this famous result called the CAP theorem that says you cannot have a system that simultaneously has consistency, availability, and partition tolerance. And so if you introduce partitions, then you would like to see that some other property should break. And Jepsen has been very successful, right? You know, if you go to this website, you can see that the author has these blog posts about bugs that he has found. And these are essentially a list of very widely used distributed systems in use today. Okay, so again, random testing seems to uncover a lot of problems in production code. So let's step back a little bit and try to see the way testing is set up. So in this talk, I will assume that testing is set up in the following way. You have a set of coverage goals, and essentially this is what you would like to cover by running tests. And you hope that these coverage goals are somehow correlated with errors that you're trying to find in your code. And you now have a set of tests. And what you do is you select a test from this set of tests. And this test covers a bunch of coverage goals. Okay? So at this point, you pick a next test. And this covers some more coverage goals. And you continue doing this until at some point you have generated enough tests to cover all your coverage goals. Okay? And what we'll call a covering family of tests is a set of tests that are enough to cover all your coverage goals. Okay? And essentially, the hypothesis is that if you can find a small covering family, this means that testing is effective because by running a small set of tests, you are able to cover all these coverage goals. And if the coverage goals are correlated with errors, then you're likely to find errors. So what does random testing do? Random testing essentially sets up some probability space over the set of tests. And then it picks one of these tests randomly. Okay? And then it picks another test, again, randomly and independently of the first test, and it keeps doing this. So now the point is that even if there is a small test covering family that covers all the coverage goals, it is not clear that just by choosing tests randomly, you will be able to find a small covering family. Right? So there is a distinction between having a small test set that is a covering family. This is really what you want. And also the fact that a random testing procedure will find such a covering family. And so this is a question that we'll explore, right? So under what circumstances can we ensure that this random procedure can find a small covering family. So in order to do this, what we'll do is the following, right? So we'll fix a specific coverage goal. And then we'll say that suppose I pick a test out of my test set at random. What is the probability that this random test is going to cover that fixed coverage goal? Okay? So this random test covers a bunch of coverage goals. Is this fixed one in it? And suppose that we can give a lower bound on this probability, right? That the test red here covers that blue goal there. And suppose that this probability is greater than or equal to p. Then our goal would be to characterize the size of covering families with respect to these parameters p and the number of coverage goals. Okay? And the key combinatorial method that we'll use is called the probabilistic method. So the probabilistic method is actually, it's a fairly common tool in combinatorics. And the idea here is that you show the existence of a combinatorial object by showing that in some suitably defined probability space, objects with that property have positive probability. Okay? So if the probability that an object has a certain property is positive, there must exist an object like that. Right? It's a completely non-effective way of proving the existence of an object. Okay, and here's the theorem that we'll prove, right? So remember that we have a set G of coverage goals. And suppose we have been able to show that if I fix a goal, then a random test will cover this goal with probability at least p. The theorem is that in that case, there is a covering family of size that goes inversely proportional to p, which is as you would expect, right? If this probability is very small, then you would need more tests. But what is more interesting is that this covering family grows with log of G, not with G. How do we show this? Well, it turns out this argument is really sort of high school probability. Well, the probability that a random test does not cover this fixed goal is at most 1 minus p, if the probability that it covers the goal is at least p. So now if I pick k random tests independently, the probability that none of them cover this particular goal is, well, by the independence, you just multiply the probabilities. Right? Now, what is the probability that these k independent tests is not a covering family? Well, it's not a covering family if you can find some coverage goal that is not covered by these tests. Okay? And just by the union bound, this is at most this much, right? Because this is just summing over all possible choices from the coverage goals, right? So this is just the union bound. Now notice that k for us has been a parameter. We have not fixed k. So now if we just pick k to be this 1 by p times log of g, we can ensure that this probability becomes less than 1. Okay, just by algebra. Okay? Now if this probability is less than 1, that says that there must exist some k independent tests that is a covering family with positive probability. Right? It's just negating the property. And the probabilistic method says, well, if something has positive probability, there must be a witness. So this just says that, well, if you pick so many tests uniformly at random, then there's a positive probability that it is a covering family. Therefore, there exists a covering family of that size. And moreover, as with many probability arguments, just by repeating this procedure some polynomial number of times in 1 by p log g, you are guaranteed that random testing is overwhelmingly likely to come up with a covering family. Okay? So the only thing that we have used is that we have a lower bound on this probability. Okay? So the combinatorics would come in proving this lower bound. Okay, so now with this background in mind, let's come back to this picture of coverage goals and tests. And whenever you design a testing procedure, the problems you have to keep in mind are, one, what are the coverage goals and why do we expect these coverage goals to be effective? So somehow you must have some evidence that these coverage goals will be good at finding some class of bugs. The second question is, what will be your tests? And what is the probability space over which you pick tests randomly. And then, as I pointed out, if you want to show that testing is effective, then a new question is, can you bound the probability that a random test chosen from this set and this probability space covers a fixed goal? Okay, so here's the plan for the rest of the talk. So I will start with some combinatorial puzzles. And then I'll connect these puzzles to testing, and then I will show how we can use some combinatorics to bound these probabilities. The reason I want to do these things as combinatorial puzzles is that if you're completely uninterested in testing, at least you have some cool little puzzles to play with. It is also to show that the combinatorics involved is not really particular to testing. It's really a general combinatorial problem. And what is nice is that these combinatorial problems, all you need is a sort of high school math background, right? Nothing really more. But they can be rather subtle. And finally, I wanted to come up with something that both formal methods and testing people can agree are cool. And of course, they are ninjas, right? So what I'll do is I'll give you a couple of puzzles, and then I'll come back and connect them to testing. So the first puzzle is called Ninjas in Training. So in a dojo in Kaiserslautern, there are n ninjas who are in training. And the way the training goes is as follows. So in each round, there are two kinds of weapons. Some ninjas are given this nunchuck, and some other ninjas are given this black blot. And then, they sort of fight against each other. And then in the second round, they're again given some of these weapons, and they again fight with each other. And what you would like to say is that the training is complete if for every pair of ninjas, you have at least one round where they have been fighting with each other, right, in opposing teams. Okay, so here's what I've said. So training is complete if for every pair there is a round where they're in opposite teams. And the question is, how many rounds do you need in order to complete their training? So there is a naive bound on n square rounds, right, for order n square. For every n choose 2, or for every pair of ninjas, have a round where they're in opposite teams, and you don't really care how the others are distributed. And your puzzle is to think about how can you do it in log n rounds, okay, where n is the number of ninjas. Right. So now you can actually generalize this by saying that, well, it's not just one team against the other, but you have k different teams, and they're all kind of fighting in a melee. Right? So now there are k different kinds of weapons. Each ninja is given one of these weapons. And then again, the ninjas with different weapons form different teams, and then they try to fight with each other. Okay? And again, you can ask the question, when is training complete? Well, training is now complete if for every k tuple of ninjas, there is a round where they are in k different teams, where they are fighting against each other. And again, the question is, how many rounds do you need to make the training complete? So just to give you some examples, so in this case, if k is equal to 3, then you can show that these two rounds are sufficient. Right? So these two rounds make the training complete, because for every choice of 3 ninjas, let's say 1, 2, 3, you see that they have different weapons in round 2. If it's 1, 2, and n, you see that again they have different weapons in round 2. If it's 1, 3, and n, they have different weapons in round 1. And if it's 2, 3, and n, they again have different weapons in round 1. Right? So these two rounds make training complete for every 3 tuple of ninjas, right? Every triple of ninjas. Is this clear? Yeah? Okay. So again, the question is, how many rounds do you need to make the training complete? And again, the naive bound is n to the k, because there are n choose k ways of partitioning the ninjas into k sets. And then for each of these k sets, you can define a round where they are in different teams. Okay? And what we'll show is that actually you can do much better. You can do something that depends exponentially in k, but only logarithmically in n. Okay? So again, this is something that you can think about. Can you find complete training schedules for these ninjas which grow only logarithmically with n? And let us say that, well, in general, we would expect the number n of ninjas to be very big and the number k of different teams to be rather small. Okay? So there is an advantage in going to something that goes, that is exponentially better in n when k is considered a constant. Okay. So that was puzzle 1, ninjas in training. The second puzzle is ninjas eating, right? So now the ninjas are hungry. So after training, the ninjas go to a beer garden, and then they're given these, they have this feast where there are different courses. And then you would call a banquet to be complete if for every pair of ninjas, there is a course that is served to ninja I before ninja J, and there is another course where ninja J is served before ninja I. It's like, you know, Martin got the first pick of the ravioli, so I should get the first pick of the brownies, right? So, you know, in some sense, we are all proud warriors. We do not want to eat always after a different ninja. So again, the question is, how many courses do you need in order to make this, you know, the ninja banquet complete? And here you notice that just 2 courses are enough. What do? Well, you give one course where you number the ninjas 1 to n, and a second course where you serve the ninjas in exactly the opposite order. Now, for every pair of ninjas, in one of them, comes before I comes before j, and in the reverse ordering, j comes before I. Okay? Not necessarily adjacent to each other, but in this ordering, j is somewhere here, and I is somewhere there, and that one I is there, and j is there. Okay? Okay, good. So for pairs of ninjas, just 2 courses is enough. What about if you generalize? So banquet is 3 complete if for every triple of ninjas, there's a course that's served in the order I, j, k. Okay, and you want this to happen for every possible ordering of 3 ninjas. How many courses do you need? Again, there is a trivial way of having n-cube courses, where you pick and choose 3 ways of picking 3 ninjas, and then 3 factorial ways of ordering them. And so that gives you roughly n cubed. So with n cubed courses, you can make this banquet complete. And what we'll show is that in general, you can do it again in log n rounds. D is a banquet is D complete if for every D tuple of ninjas it is complete. And so there will be an exponential dependence on D, but only logarithmic on n. Okay, and in fact, this is the best you can do. So again, you can try to think of this in case of a 3 complete banquet. How would you assign sort of log n rounds of courses so that you get 3 completeness? Okay, but of course, you can make this problem a little bit harder by having the hierarchy of ninjas, where the master always gets fed before the student, right? And so you can imagine that these ninjas are arranged in some partial order, and if you're higher in the partial order, you get fed first. So now with pairs of ninjas, again, 2 courses suffice, because you can imagine that you have this tree, if the hierarchy is a tree. If you have this tree, then you can just do a left first depth first search, and then a right first depth first search. And again, you can show that you have this property that every possible I, j, there is an ordering where I is before j, and another where j is before I, if that is allowed by the hierarchy. Okay. And you can sort of generalize this to say for every admissible triple is there, there should be a course that's served in that order. Okay, so again, the naive approach is polynomial, so n to the d in general, but as we shall show that you can do this in log n rounds. Right, so those were the puzzles, and let's now come back to testing. So what is the connection between these ninjas and testing? Well, here's the connection between the training ninjas and the Jepsen style distributed systems testing. So ninjas are the nodes in your distributed system. The weapons are really a partition of the network into k different pieces, right? So for example, all the ninjas with the nunchucks are in this part, and we'll assume that they cannot communicate with all the ninjas with this other weapon here, right? So a partition that's induced by Jepsen is exactly, as a training round for the ninjas. So what's a test? So a round corresponds to a test. And a test is how you pick this partition, what weapon you give to each of these ninjas, or which block in the partition do you assign each node. And then a complete training is essentially a covering family of tests. It's a splitting family of partitions, where we define the coverage goal of splitting families as, well, I'm given n nodes and some fixed k, and I want to partition these n nodes into k different blocks, such that for every k tuple of nodes, there is some partition where each of these k nodes are in different blocks. If I want to test a system against partition tolerance, I would like to have a test where the application server is in a different partition than the database server. Right? I would have another test where the zookeeper node is in a different partition than the database server, and so on. And so this coverage family essentially says you want to find partitions that separates out every possible kinds of nodes. Similarly, I can go from the eating ninjas problem to testing concurrent systems. So here the ninjas are events in an asynchronous program. The hierarchy is essentially the partial order that's induced by the underlying concurrency model. The tests are schedules or linearizations of this partial order. And a D-complete banquet is essentially, D-complete banquet corresponds to a coverage notion of a D-hitting family of schedules. Okay? And the definition here is that I give you a poset of events, and I give you D events, and I want to make sure that the schedule that I run schedules these D events in exactly this particular order. Okay? And so the notion of coverage is that I would like to cover all possible orderings of D events in this asynchronous program. So why are we looking at these somewhat esoteric notions? Well, it turns out if you look at the bugs reported by Jepsen, most of them essentially correspond to a small number of partitions of the network, right? 2 or 3 or maybe 4. So here's a complicated bug in Kronos, which is a distributed job scheduler that Jepsen found. So Kronos is a complicated distributed system with several layers of quorum. And so it has some zookeeper nodes which ensure consensus at some level. It has these mesos nodes which deal with resource allocation. And then there's Kronos that handles the job scheduling. These are all self-distributed in the system. And there's a Kronos leader, a mesos leader, and zookeeper leader. Okay? And in order to show a bug in the system, well, what Jepsen did was to isolate the zookeeper leader from the mesos and the Kronos leader. Okay? And there's actually quite an interesting story on GitHub, right? So you see that this guy who wrote Jepsen, Kyle Kingsbury, so he goes and talks about all these bugs on the GitHub pages of these projects. And there he first reports this bug on the 7th of August. He says, well, if I partition Kronos from the zookeeper leader, then the system crashes. And then there is some discussion among the developers and say, well, this is expected behavior because, look, you introduce partition tolerance, and of course, if you cannot have consensus, it's great that the system crashes, right? So we give up availability, okay? And so this is the right behavior. Okay, so about a week later, he says, but now I can find a case where it does not crash, right? You just told me that it should crash, right? So, and if you follow Jepsen, then you will see that he has all these detailed discussions with developers. And most of the time, the guy is right. He finds problems with these distributed systems. Right. So the other notion was D-hitting. And why are we looking at this? Well, it turns out, just empirically, that there are many bugs in asynchronous programs that involve a small number of reorderings of certain events, right? So, and there are many different papers, including some by Martin, that showed this, right? So, for example, if you have these concurrent programs, then the ability of ordering or looking at every pair of events and reordering them corresponds to very simple race condition-like behaviors. Then, if you have 3 of them, then this is like an atomicity violation, where you expect these 2 things to happen atomically and then something else. But in a bad case, this something else comes in the middle. So again, if you could find tests that cover all possible orderings of a small number of events, you're likely to find these bugs. Okay, so those were our coverage notions. Now, going back to what we started out doing, we would like to bound the probabilities that a randomly chosen test covers a fixed coverage goal for each of these notions of coverage. Okay, so we'll do this. Okay, so let's first start with the splitting families. So we fix some k-element set S, and now we pick a random partition of these nodes. And our question is, what is the probability that a random partition of the nodes, n nodes into k blocks, will split this particular set? Well, again, we can work this out using sort of high school math. Well, if you think about a splitting partition, then this really corresponds to a map from the rest of the elements, the n minus k elements, to these k elements. Okay, so you have k elements in S, so think of them as forming their own partitions. And now what you need to do is take the n minus k remaining elements, and for each of them you have to map them to one of these k representatives. Right? So if you do this, then you get a k partition that separates all the elements of the set S. Okay? How many possible things are there? Well, there are k to the n minus k such maps, right? Because there are n minus k elements, and each element can be mapped to k possible outputs. Okay? Good? So the probability that this particular set S is split by a random partition is essentially the number of possible ways, the number of partitions that split this set, divided by the total number of partitions. Now, the total number of partitions of n things into k elements has a name. It's called the Stirling number of the second kind. And this is something that has been studied quite a bit in combinatorics. So this is essentially the number of partitions you get into k different pieces. Right. So the probability that a fixed set is split is this. Now, what would be nice is if we could get rid of the dependence on n in this expression. And the reason is that, well, remember that what we would like to get is something that depends on p and on log n, right? And if the probability has this n here, then there is an n term showing up in the number of tests that you need. So can we get rid of n? Yes, we can, by another combinatorial argument that says that k to the n is at least as big as k factorial times the Stirling number. Why is this? Well, k to the n turns out to be the set of all possible functions from n elements to k elements, right? That's the number of such functions. And this expression on the right turns out to be the set of all surjective functions from n to k. Why is this? Well, each surjective function from n to k induces a partition of the n elements into k different blocks, right? So the inverse of the first, inverse of the second, inverse of the kth. And then for each choice of k elements, you can order them in k factorial ways, right? So you get this simple combinatorial inequality. Now you can plug that back in to see that the probability that a fixed set is split, now completely in terms of k, is roughly k factorial divided by, well, actually, k factorial divided by k to the k. Okay? And at this point, I can get this general hammer of this probabilistic method and say that there is a k-splitting family of size, this 1 by the probability, times log of the number of coverage goals. The number of coverage goals is approximately n to the k, right? The number of possible sets of size k. So if I take the log of that, there is a k log n. Okay? So this shows that there is a small family, and as we argued earlier, that random testing is very likely to find this small family. And perhaps this is one way of explaining why Jepsen works so well, right? So just by running a small number of random tests, you are overwhelmingly likely to cover all possible splits of a distributed, of the nodes. And empirically, it turns out that a small number of splits is good enough to find many of these bugs. Okay, so there is a little bit of a technicality. So it turns out that uniformly sampling these k partitions is not so easy, but you can sample based on balanced partitions where most of the sets have the same size. This is sufficient. And it turns out that the combinatorial arguments in this case are somewhat harder. And in particular, there's an interesting story here that at some point we came up with this inequality that we had to prove. So we tried for some time, we were a little bit stuck. And then we figured out that this was one of the problems given in the American Mathematical Monthly in February this year, right? And it turned out that Philip worked out a very nice combinatorial argument based on these tests, or these insights from tests, that lets you prove this inequality. And so it was a happy ending. Okay. So now let's go back to the other case that we looked at, the hungry ninjas problem, or the equivalently the small d-hitting families. And here again, to show that there is a small d-hitting family, we can use very simple combinatorics. So suppose I fix a tuple of d ninjas. So now remember that a test in this case is just a linearization of these n elements. So what is the probability that a random schedule, a random linear ordering of these n elements hits this particular d tuple? Well, this is 1 by d factorial, right? Because these d elements can occur in any one of d factorial ways in this random order. So the probability that this particular ordering occurs is 1 by d factorial. Okay? So what is the probability that if you pick k such schedules uniformly at random, that none of them cover this particular ordering? Well, it's the product of the probabilities. It's 1 minus 1 by d factorial to the power of k. So what is the probability that these k schedules are not a hitting family? Well, there are about n choose 3 ways of choosing this, times the probability that at least one of them is not covered by these k tests. Okay? So again, the union bound. And so just by picking k to be this function, so it's some exponential function of d, but logarithmic in n, you can make sure that this probability is less than 1. And again, by the probabilistic method, this shows that there exists a family of xd log n that is a hitting family. Right. So I've shown you these two examples of how we can bound these probabilities. Let me now pop up a little bit and show some combinatorial connections, right? So I think that some of these ideas that we have been working on have appeared in different forms. So for example, this splitting families shows up in these theoretical constructions of perfect hash functions. For example, there's a rather old paper by Andy Au, which uses something like a k-splitting family to construct perfect hash functions. And then there has been some follow-up work, including some very deep work by Fredman, Komlosh, and Shemereddy, and where one of the goals was to construct explicit families of these k-hitting sets. Okay? So notice that what we have shown is an existence result and a random construction. Right? We said that if you pick things at random, it's likely to be a k-hitting family or k-splitting family. We have not given an explicit construction of such a family. Getting an explicit construction turns out to be very, very difficult. And this is actually quite a recurrent theme in combinatorics, where sometimes you can use the probabilistic method to show something exists, but actually finding an explicit instance of an object is much more difficult and happens many years later. So that's about splitting families. It turns out there is also a very rich history of combinatorial results related to the hitting families that we talked about. And this is related to the order dimension of a poset. Right? So the order dimension of a poset is essentially the smallest number of linearizations of the poset, such that the intersection of all these linearizations is the original poset. Okay? And there are many different characterizations of the order dimension. It's the smallest dimensional Euclidean space where you can embed your partial orders so that the natural ordering on vectors corresponds to the ordering on the partial order. Right? So you can show that these things are equivalent. And they have been studied for quite some time, and there are very deep and sophisticated results known about them. But it turns out that this d-hitting families is a natural generalization of this order dimension that was not studied before. Okay? So there are also some hardness results for these order dimension for general partial ordered sets and so on. But it turns out that this notion of d-completeness, where instead of looking at pairs, you look at d-tuples, is somewhat new. And we are quite sure that there are other nice combinatorial results to be had in this space. Let me come back to this question of explicit constructions again. So as I said several times already, that we have shown the existence of these methods, and we have also argued that a random search procedure is very likely to find these families. But we have not given explicit methods. Now, it turns out that this probabilistic method may not always give you an optimal result, right? So, for example, there is a two-splitting family of size log n. This was your first puzzle. And the way you find a log n size family is that if you have n elements, just look at the log n bits and have a round where for each bit, all the elements that have bit 1 in that position is in one side, are in one side, and all the elements that have a 0 in that position are on the other side. Okay? Then you get log n rounds, and you separate out every pair. Okay? Now, if you work through the combinatorial argument, that is this thing for the general k, we get a bound of 2 log n. Okay? So you see that the probabilistic method may not always give you an optimal combinatorial construction. On the other hand, it's within a constant here, so it's still quite good. So similarly, there are other techniques. For example, for de-hitting families, in case the partial order has these constraints, the partial order is a tree, we have explicit constructions that show that there is always a hitting family of roughly this size where h is the height of the binary tree. We do not know if this is optimal. And also, we do not know a probabilistic construction that gets to this bound. Okay? So, it can be both ways, right? In some cases, you can directly find an explicit construction that is small, and it may not be clear that random testing is likely to find that specific optimal construction. On the other hand, for some other cases, matching explicit constructions are not known. For example, for case-splitting families, Yao's result shows that there are case-splitting families of roughly this size. And you don't have to go through the exact numbers. It just says that this number is actually higher than the probabilistic construction that we have given. Okay? So I think there is a nice space of problems here in relating these combinatorial constructions and the probabilistic constructions and shifting them back to testing. Okay. So let me summarize. So when we design testing procedures, we talk about what are the coverage goals that we want to cover and what set of tests are we going to produce. Okay? And in random testing, we also talk about how do we generate these tests randomly. And now the argument that we make in our paper is that if you would like to prove theoretical results about the effectiveness of testing, one additional question you might want to ask is whether you can bound the probability that a random test covers one of your coverage goals. And if you can give a lower bound on this probability, then you can give a general argument that essentially shows that there's a small set of tests that you can find that will be good enough to give you full coverage. So we saw 2 examples of this. One was the splitting nodes in network partitions. The tests were network partitions, and we showed that you can find a bound on this probability, which is exponential in k, but logarithmic in n. And empirically, k is usually very small, n is quite big, right? So in a distributed system, n is a total number of nodes, and we can find a lot of errors, a lot of bugs in these programs with small 2, 3, or 4 partitions. The second example was hitting all possible orderings of d tuples in an asynchronous program. Here, the tests were schedules or linearizations of these events. And again, what we could show is there is the probability that a random test, a random schedule covers a specific d tuple depends exponentially on d, but only logarithmically in n. And again, in an asynchronous program, you would expect that the number of events n is much larger than the d, which is the number of the bug depth that you're looking for. And so, moving back up, the natural question is, can we use these methods in other places to show some theoretical results about the effectiveness of random testing? So we started by saying that random testing is very effective. Unfortunately, we have very few results that theoretically justify why random testing is effective. And this is, the two examples I've shown you are specific cases where we can show these theoretical results. But it would be nice to explore if there are other situations where we can also give such theoretical guarantees. I do not think that we can give one theorem that shows the effectiveness of random testing in all possible scenarios. And in fact, we can give examples where random testing is going to be ineffective, and a carefully constructed explicit set of tests will be much better. But it would be nice to see more results in this spirit. So that's all I have to say. Thank you. And this is work that is mostly in Philip's PhD thesis. So you should look out for that. And thanks also to Philip for working on some of these slides, because I hurt my hand. Thank you very much. I'm happy to take questions.
Thank you. Questions? Yeah, Mikko.
Hi. It's quite interesting work. I missed the initial part of the talk, so sorry.
We can do it again.
Okay, great. So whenever you consider schedules, do you consider linearization of an anti-chain? Or
No. So the anti-chain was the simpler version that I did in this talk. So in general, we look at schedules of arbitrary partial orders.
Okay.
We have good results, this of log n dependence only for trees. We know that for arbitrary partial orders, we cannot get such log n dependencies. And now Philip has some new results that I did not talk about that talks about arbitrary partial orders.
Oh, okay, also. Thanks.
Okay. Yeah.
So here your tests were generated independently, but is there any point in looking at cases where there is a stochastic process that's generating the tests? So basically you generate one test and then you have some memory of that when you're doing the next generation. And do you see any hope of getting any results there?
So this gets very close to showing this kind of Markov chain Monte Carlo cover times and so on. And usually in directed state spaces, most results are negative, right? So you don't get very good bounds for cover times. But yeah, there may be. I know that there's an old paper by Christos Papadimitrou and Milena Mihail that explores some of these questions.
I was wondering, how, in concurrency analysis, at least, some of the results on these bounds and so on were by Lacerson's group, right? The series parallel cases, when it happens before is of certain shape.
Yes.
And recently there is results. Mitko did some work, and then there's other people work on this two-dimensional partial orders, another kind of structure. So I was wondering, in the second half, can you get better bounds if the happens before is of a certain structure for certain class?
Yes, so the results that we have are mostly in that spirit. So for example, we can do it for trees, we can do it for series parallel graphs, which comes out of silk, right? So,
yes.
So we have explicit constructions for hitting families when you have series parallel graphs.
But okay, it's interesting to see if this latest two-dimensional partial orders, the generalized series parallel graph, whether it holds there as well.
So this I do not know, but I know that you cannot get a good result or we do not know how to get a good result for general partial orders, and there are actually some hardness results for order dimension for general partial orders.
It's just light generalization, but covers pipeline parallelism. So
I see. So
it could be interesting. Take a look.
Okay.
Any other questions? Well, if not, then I have a final one. So it was not quite clear to me how your theory explains the success of Jepsen. Does that mean that it doesn't matter when a partition occurs, for how long it occurs, and all these things? Is this not relevant as well?
No, so I didn't get into the exact thing. So the way Jepsen works is that it usually sets up these things. It runs a small number of operations. Then it introduces a random partition, and then another set of operations. And these operations are also chosen randomly. So now, in addition to the bounds that I showed, there would be another multiplicative bound on the number of possible things that you can do in the front and in the back. But again, empirically, the number of operations you do to set the stage is usually much smaller than the number of nodes, right? And similarly, the number of things that you do afterwards, right? So for example, you would say, oh, let me write some values to all the different nodes, then we introduce a partition, then I try to read, right? And you can take into account those things as well in the bound. Right? So the paper has some more details. I did not put all the algebra here.
Okay, so thank you.